Hi, this is the second part of the NEET 2025 question paper discussion, and we are starting with the 52nd question. First section, there were 6 questions only we have discussed to make them brief. Now, the 52nd question, which is from organic chemistry, you may classify it as either with the haloalkane where we study about Grignard reagent, or you can classify it in the chapter aldehyde ketone, etc. because here the reaction is between Grignard reagent and a keto group. Okay, see, we have this compound. It is having an aromatic compound having carbonyl group as well as cyano group, and you are first treating it with the methyl magnesium bromide. It is mentioned that you are taking its excess, and then you are hydrolyzing it, and what is the final product? See, if you remember, we know that a Grignard reagent reacts with a formaldehyde to give a primary alcohol. Any other aldehyde would give a secondary alcohol, and a ketone would give a tertiary alcohol. Okay, so what really happened? The Grignard reagent add across this carbonyl group, nucleophilic addition, the slightly minus charged, partially minus charged alkyl group, here it is methyl group, get attached on the positive center carbon, and MgBr get attached on the oxygen, making this a single bond. And the subsequent step of acidic hydrolysis, it hydrolyzes away MgBr and gets you an alcoholic group here. But since it is not one mole proportion taken here, because methyl magnesium bromide is excess here, we know nitrile group also reacts with the Grignard reagent. Here also we know that nitrile group is like this, C triple bonded, isn't it? It attaches magnesium and MgBr, methyl group and MgBr like this. Which in the subsequent stages get hydrolyzed, whereby this group is removed and a carbonyl group is introduced. So that group becomes carbonyl group. The cyano group becomes carbonyl group. Okay, so the expected product will be having an alcoholic group here and a keto group here. So we will go through the options. Here the carbonyl group remains as such, so that is not the answer. Here it is converted to a tertiary alcohol, so that's a possibility, and that N butter still remains as nitrile group. In the excess of in the presence of excess of methyl magnesium bromide, that is not possible, so that also cannot be the answer. Here look, CS3OH, COCS3, both expected changes have happened, so 3 could be the answer. And what is the last possibility? There you look, this group also further reacted to form a tertiary alcohol. Will that happen? Remember, in the first stage only the first methyl magnesium nitride gets added across the nitrile group, MgBr. A second molecule of CS3-MgBr will not attack at this stage. It is then subjected to hydrolysis, acidic hydrolysis, to convert this to keto group. Of course, if you that is, this product is formed, isn't it? Only if you take this out from the presently aqueous medium, then dry it and again treat with the Grignard reagent, that will get converted to this. By simply taking excess Grignard reagent and then treating with the acidic water will not provide this, because we know if excess Grignard reagent is there, it will react with the aqueous medium, producing the parent alkane here, methane. Methane will be produced. Grignard reagent will be decomposed. So in a single stretch, you won't get this product. Of course, you can convert this to this in a separate Grignard's reaction. Okay, so Don't think that this will further react and produce that. It is not happening here. The product will be here. Okay, so our answer is not 4 but 3 in this particular question. Okay. See the next question, question number 53. This is also from organic chemistry, and the question discusses about geometrical isomerism. You are asked to find out which among the following these 4 compounds shows geometrical isomerism. Okay. See, the 4 options given are 1,2-dimethyl cyclohexane, 2 pent-1-ene, 2-methyl hex-2-ene, 1,1-dimethyl cyclopropane. Listen, they have given in the question only the formula name. They haven't given the structure or formulae. So it is a pure risk that you have to draw the 4 structures without any mistake. Okay. 1,2-dimethyl cyclohexane, 1,2-dimethyl cyclohexane, pent-1-ene, 1, 2, 3, 4, 5, pent-1-ene, 2-methyl hex-2-ene, 2-methyl hex-2-ene, 1, 2, 3, 4, 5, 6. Then lastly, 1,1-dimethyl cyclopropane, 1,1-dimethyl cyclopropane. Okay. Now see, to exhibit geometrical isomerism, double bond is not a must always. You have to remember, geometrical isomerism can be shown by compounds having double bond or having a cyclic structure, or even in coordination compound, or in cumulated double bond system, etc. So what is the only criterion required? One orientation should not change to the other. There are 2 possible orientation. One orientation should not change to the other by itself. So there must be some restriction in the free rotation. Okay. Here, coming to the case of 1,2-dimethyl cyclohexane, the cyclic structure is a restriction. It does not allow free rotation with respect to the single bond. Even with the single bond, there is no free rotation. This CH3 cannot go over there, and this H cannot come over here by itself without breaking the ring. So see here, I have drawn cis variety because CS3 towards the observer, both CS3 towards the observer, both H away from the observer. So it is the cis variety. Equally, you may have one of the CS3 to the other side and H to this side, but CS3 on this carbon again towards you, means the trans variety. 2 methyl groups are directed in opposite directions. Okay, so it can be cis or trans, means the first compound is having geometrical isomerism. Hope you understood that. So this will be our answer, but we will have to check the others also. Okay. The next one, pent-1-ene. It is having double bond, but having double bond alone is not necessarily be a geometrical active compound. See here what happened. The terminal double bond. When the double bond is terminal, and also when both the groups are the same on this terminal carbon, it cannot show geometrical isomerism because exchanging these 2 does not provide you with a new variety. See here, of course, on this carbon, it is one is hydrogen, other is a propyl group. Here the requirement is satisfied, but here the requirement is not satisfied, so this cannot show geometrical isomerism. Coming to this one, 2 hexene with the methyl group on the second carbon. The positioning of the double bond on a non-terminal carbon does not guarantee you that the compound is geometrical isomer, having geometrical isomer. Why? See here what happened. Due to the presence of 2 methyl group on the second carbon, both the groups on this carbon became identical. So again, it fails to show geometrical isomerism, even though on this carbon there are 2 different groups. One is hydrogen and the other is propyl group. But no use, because here the 2 groups are the same. So this compound also cannot show geometrical isomerism. And finally we have the 1,1-dimethyl cyclohexane. Even though 2 methyl groups are there, they are on the same carbon. So that does not make any difference. Whether you arrange like this or like this, a new orientation is not resulted. Because on this carbon it is both hydrogen. So you cannot get a new variety. But never attempt to change group like this and produce geometrical isomer. That you can do on the board only or on the paper only. Because if you do like that, it is no more a stereoisomerism but a structural isomerism where methyl group is exchanged among carbon atom, different carbon atom. That is not supposed to happen during the verification whether a compound can show geometrical isomerism or optical isomerism. You are not supposed to do like that. So to conclude, this cannot have geometrical isomerism. So we can confirm that 1 is our answer for the 53rd question. Okay, hope you understood that. See the next question, 54. It is from Basic Concepts of Chemistry. Here they have provided with 5 samples of different compounds, and you have to identify which among them have same number of atoms. Same number of atoms. Okay, arithmetics. See, to verify number of atoms are the same, you need verify number of moles of atoms are the same. When number of moles of atoms are the same, number of atoms are also the same. So the convenience of doing like that is that you don't have to bring Avogadro number and multiply with Avogadro number, etc. You can avoid using Avogadro number then. Simply verify their moles of atoms are the same. Okay. First case, 212 gram sodium carbonate, Na2CO3. You have to find the number of mole of atom in that. For that, you have to first divide mass with the corresponding molar mass. Here, for all the compounds, they have provided the molar mass in the question paper so that you don't have to spend time to find the molar mass. Okay, that much useful. Okay, so 212 by molar mass of Na2CO3, 106. Now check, each molecule is having one Na2CO3, 6 atoms. So to get the number of moles of atom, you have to divide. This gives you number of moles of molecule. Into number of atom per molecule gives you number of moles of atom. Number of mole of molecule into number of atom per molecule gives you number of moles of atoms. So 212 by 106 into 6. 12 gram atoms of atoms are there altogether. The second case is 248 gram Na2O. Same method. 248 divided by molar mass 62. Each molecule is having 3 atoms. Multiply with the 3. Again, simple calculations. You can easily get it. You again get a 12 gram atom. Third case, 240 gram NaOH. 240 divided by molar mass, familiar, 40 into 3 atom per molecule. 3, 18. Okay. 12 gram hydrogen. 12 divided by molecular mass, 2, 12 by 2. But each molecule is having 2 atoms. 12 by 2 into 2, 12. Finally, we have 220 gram CO2. 220 divided by molar mass, 44. Each molecule 3 atom. 15. So you have to verify which all cases are having the same number of atom or same number of moles of atom. Here it is A, B and D. A, B, D. A, B, D. Such a combination in the given options is 3. So for this question, your answer is 3. Okay. In the next question, which is 55. See, this is from chemical bonding and molecular structure because it is comparing the bond strengths. What are they? Listen, here first structure is this, where you have to consider the CH bond in benzene ring. Here, benzene ring with an ethynyl group attached to it, and you have to compare the strength of CH bond in this particular case, this CH bond. And the third is a propene, where you have to compare this CH bond strength. You have to arrange Roman 1, 2 and 3 in the decreasing order of their bond strength. See, we know that an sp hybrid carbon has smaller hybrid orbital with a more effective overlapping with the hydrogen atom, and so shorter the bond, stronger the bond. Hope you understood. sp hybrid orbitals are more spherical, near to more spherical shape. So overlapping with the hydrogens, s orbital will be more effective, bond will be shorter and stronger. So we can expect that this CH bond in the second case to be the strongest one. Then what about this? It is double bonded carbon. So compare this with this. Here it is an sp hybrid carbon. You have to remember, here it is an sp hybrid carbon. Here it is an sp2 hybrid carbon, and here it is an sp3 hybrid carbon. So here sp2 carbon versus hydrogen bond. So that will be comparatively less stronger. So one will come the second. And third is an sp3 hybrid carbon with more P character, 75% P character. So CH bond will be comparatively the weakest here. So third will be 2, 1, 3 will be the answer. So 58 answer among the given option, 2 will be your answer. Okay. Next is 56, question number 56 from thermodynamics, a numerical case, a somewhat a difficult problem also. Okay, we will attempt that. See, in this particular problem, you are asked to find out the enthalpy change for the reaction Ba giving Ba2 plus aqua plus 2E minus. Ionization of barium in aqueous medium. And you are provided with the enthalpy changes of 3 other reactions. So from the enthalpy changes of the non-reactions, from the non-enthalpy changes of some reaction, you have to find out the unknown enthalpy change of some other reaction. Okay. See, the very question has a slight mistake that they have asked you to find Ba2 plus, but they haven't mentioned aqua. Actually, they should have mentioned it is aqua, because only if it is aqua we can solve this problem. See, you have to remember in thermodynamics, Ba giving Ba2 plus gaseous state, Ba giving Ba2 plus aqueous state, they don't have the same enthalpy change. Okay, so it must be specified what is becoming what in which state. That not mentioned. Actually, only when it is aqueous the answer could be found out. So I taken to be granted that it is aqueous. Okay, and once again, once we apply Hess's law, many times get cancelled. No, for cancellation you cannot cancel X solid with the X gas, or half X2 solid with the X solid. They won't cancel because thermodynamically they are different. Even though atomic wise they may be same, but thermodynamically they differ. They suggest two different energy states and so will not be cancelled. So here we involve so many cancellation, etc. So everything must be clearly specified whether they are solid, aqueous, gaseous, etc. That's the importance of so that's the thing we have to take much care about while solving thermodynamical problems of this kind, where we apply Hess's law. Okay. See, you have to find out. So this is the pattern. First you write Roman 1 required equation. This is a systematic approach. Roman 1 required equation. Ba solid giving Ba2 plus aqua plus 2E minus semicolon delta H, which you have to find out, unknown. Then Roman 2 given equations. See, in the question they have only stated things. You have to carefully, without making any mistake, express them as equations. One statement they have given is standard enthalpy of formation of sulfate ion aqua. So we are writing delta formation H standard 0, H standard sulfate aqua. See how it will be formed from the elements sulfur solid plus 2O2 gas. You shouldn't write 4O because 2O2 and 4O are thermodynamically not equal. 4O is having more energy, 2O2 is having lower energy. Here, since it is standard enthalpy formation, you have to express it as 2O2 gas plus 2E minus, giving SO4 2 minus aqua semicolon delta standard H1 minus 216 kilocalorie per mole. That value is given. I have written the unit there to kilocalorie per mole. Second statement they have given enthalpy of crystallization of barium sulfate. Crystallization happened from aqueous solution. So delta formation H0 Ba2SO4 Ba2 plus aqua plus sulfate ion aqua giving BaSO4 solid precipitation delta H2 minus 4.5. Heat is released. And they have also given the standard enthalpy of formation of barium sulfate. Delta Fx BaSO4 Ba solid plus S solid plus 2O2 gas giving BaSO4 solid delta is 3 minus 349 kilocalorie per mole. So now what to do? Second stage is over. Required equation Roman 1, given equations Roman 2. Third, operation. How to get the required equation from the given equations. Look here, Roman 3 operation. What I want first, I want barium solid on the reactant side. You scan these three given equation and find where Ba solid is on the reactant side. No. Here barium solid is on the reactant side. So I take the equation 3 as such operation. Equation 3 is taken as such. Then what I want? Ba2 plus on the product side I want. Scan them. Yeah, here it is. Ba2 plus is here. But it is on the product side. Whereas I want it on the reactant side. So reversed 2 I take. Plus reversed 2. Okay. Don't worry about any other thing for the time being. I want 2 electron on the product side. Go through. Oh, this is having electron, but it's on the same number as required, 2, but it is on the reactant side. So think about reversing it also. So 3 plus reverse 2 plus reverse 1. That is the operation I am going to do. What about all other species? In most cases, they get cancelled. Okay, we will verify them. Okay, for our own satisfaction, we verify are they getting cancelled. Otherwise, we are not going to get the answer. See what to do. Operation. I have drawn a line here. On this side, we write reactant. On this side, we write product. First thing what to do, 3 has to be taken as such. Look at equation 3, this one. So these 3 reactant I write on this side. Ba solid plus S solid plus 2O2 gas. On the product side, I write BaSO4. Okay. Now what I have to add? Reversed 2. I have to add. Reversed 2. So this I add on reactant side. I added it on the reactant side. These 2 on the product side, because here reactants are product. These 2 on the product side. That is also over. Now reversed 1 I have to add. Reversed 1. So product is added on the reactant side. The 3 reactants are added, including electron, is written on the product side. Now what we have to do? We have to cancel identical terms. Okay. Let's again scan this collected equation. Ba solid. I check. It is nowhere excess on the reactant. If there are 2, we have to add them and write 2Ba. It didn't happen here. Here there is any Ba solid. No. So Ba solid remain uncancelled. Now sulfur solid here. Yeah, here is a sulfur solid. Here is a sulfur solid. I have to cancel them. 2O2 gas. Yeah, here is a 2O2 gas. I cancel them. BaSO4 solid. Cancel. Sulfate ion, aqua. Sulfate ion, aqua. I cancel. So what? Now nothing remains to be cancelled. Ba solid giving Ba2 plus aqua plus 2E minus. That's the thing what we require. Ba solid, Ba2 plus 2E minus. So what the operation we have performed is perfectly correct. We got the required equation correctly. Okay. Now what to do? Last stage, Roman 4, calculation. 1 required equation, 2 given equation, 3 operation for calculation. What is delta H? Do the similar operation on delta H values. 3, so delta H3. Reversed 2 means minus delta H2. Plus reversed 2 means minus delta H2. Plus reverse 1 means minus delta H1. If it is as such, you have to add them. Plus delta H2, delta H1. But here it is reverse or minus. So delta H3 minus delta H2 minus delta H1. Minus 349, the sign as such in the given equation, minus 349. Minus 216, so here it is 2 plus 16. Minus 4.5, it is 4.5 here. So you get minus 128.5 kilocalorie per mole. So that's the answer. Among the given option, 2 is our answer. Hope you understood that. Okay, go through this explanation more than one time to have a clear picture if you didn't understand while you hear for the first time. Okay. The next question is from redox reaction first year chapter. Okay, regarding oxidation state. You are given 3 compounds KO2, H2O2, H2SO4 and you have to find the oxidation state of the underlined element. Here it is K that is underlined, here it is oxygen and here it is sulfur that is underlined. KO2 is a superoxide and we know oxygen has the specialty there because O2 has a common minus 1 charge. So each oxygen is minus 1 by 2. But here it is not that of oxygen it is asked. It is of K that is asked. We know it is plus 1. Potassium, with whomever it may stand, takes the oxidation state of plus 1 only, isn't it? So that is plus 1. And H2O2, you know its structure to be like this, where each oxygen is minus 1 only. Due to OO single bond, it doesn't require minus 2. So here it is minus 1. Underlying element oxygen is minus 1. And H2SO4, we know the method to find the oxidation state of sulfur. Let hydrogen be plus 1, we know. So 2 hydrogen plus 1 into 2 plus sulfur being unknown X plus oxygen being known to be minus 2, 4 into minus 2. They together make up the molecule neutral, so it is 0. So 2 plus X minus 8 is equal to 0. X minus 6 is equal to 0. So X is equal to plus 6. Sulfur is in the plus 6 oxidation state. So it will be plus 1 minus 1 plus 6 here. Plus 1 minus 1 plus 6 here. Here option 2 is our answer. So that's an easy one from redox reaction. Only prone mistake is you may think that it's of oxygen. You may go for minus half there saying that. But such an option is not given. So you will rethink. So you will mostly come to this conclusion only, the correct conclusion only. Okay.